Okay, so first, thank you for having me here. I'm gonna present a project we did some time ago about offloading MPI tag matching into the network. We call this optimistic tag matching approach. And there was a work I did while I started at the University of Olmos. Like, that was my first publication for the PhD. And well, we did it with a lot of people, like with Torsten included, like a lot of people from NVIDIA. So this work was a lot of effort. So what I want to introduce here is what is this project in general and what we've done through our work. So what is the goals we want to fulfill with this work? So we had one first goal, which was completely offload MPI tag matching to the network. In this case, I put here including unexpected messages because certain approaches don't handle them because it's a bit more complex. But our goal from the beginning was to offload everything. So this has two extra goals that it generates. But the first one is we save CPU cycles. Everything is going to be offloaded from the CPU to the network. In this case, so the CPU is completely removed from the equation, which is exactly the third point. We remove the CPU from the network GPU data path. This is extremely important and super interesting, as it allows us to change how we approach GPU-centric applications, which are very important in HPC nowadays. So I've been talking a bit about tag matching in general, but I'm gonna level up, and this is what I'm gonna be calling traditional tag matching, which is the traditional quote-unquote approach tag matching is being done before on MPI communications. So tag matching is this process we have in MPI that enables the point-to-point communications. It has some constraints, it got some guarantees so application developers can rely on certain parts of how this process communicates to each other for their applications. Typically, it's been done having two queues, which is the unexpected message queue, which here we store messages that you receive before you were expecting them. And then we have the posted receive queue, which is the messages you are expecting to receive. So for these two queues, the receiving and posting receives flows are the following. So for receiving messages, the flow is the following. Let me put the pointer here. So first, when we receive the message, we have to try to find a possible match. That means we posted that receipt before. So we search in the PR queue, and in the case we find a match, we remove that entry from that queue and we handle the protocol and we mark the message as received. In the case the message we receive doesn't have a match in the PR queue, we add the message to the unexpected message queue, and then we successfully mark that this has been handled, but the message hasn't been received. Then we have the other way around, which is when we request a message or when we post a receive, we do kind of the opposite way. So then we try to find a match in the unexpected message queue, which would mean like, okay, we received this message before we were expecting them. So in that case, the message has already been received. So we mark that I've received. So we take it from the list, we say we handle protocol, message received, perfect. And then again, if the message if the posted receive doesn't have a match, we put it on the list, and eventually we're gonna be matching that in the receive message. So this is how the flow of traditional tag matching works. But at the same time, MPI has some constraints we have to fulfill with this method, with tag matching, which are the following two. The first one is the order of posted receive. It mostly says that when you receive a message from the network, which receive is the one to be matched to. So in this case, this constraint says that the receive that has to be matched is the one that was posted first. Okay, so then now we have the second constraint, which is not overtaking on messages. This is kind of the other way around. So when we have multiple messages coming from the network from the same source, that can be matched to the same receive. We have to match to the message that arrived first, the message that was sent first. So within the same sender, the messages don't overtake each other. Okay, so as you can see here, with the flow and these constraints, the most easy way to implement all of this will be with queues. But queues are not very performant when you have to match, because this is done per message you receive or post. So this is not very efficient when you have a large number of messages. So what is there in the literature to kind of solve or help this in this issue? So there are two main strategies in the literature. The first one are what we call software strategies that are either in two groups. The first one is redesigning how these tag matching data structures are used or which data structures are used. So here I've said the traditional tag matching uses queues, but you can use hash tables. This is a bit of foreshadowing for how we did optimistic tag matching. But you can use hash table or other data structures to try to feel better how that matching works. Also, there are approaches that dynamically change how tag matching is done. So let's say you have an application that has a low message rate or any other particular thing you care. And you should be able to tweak to say, okay, when this condition is fulfilled, I want you to use traditional tag matching. But now that I have more message rate or this other thing, I want you to use an approach that is hardware offloaded or one of the redesigned ones using hash tables. On the other side, we also have what is called hardware strategies, which again, they are divided into kind of categories. The first one is completely offloading tag matching or traditional tag matching into an accelerator. So here we don't make any assumptions of how our accelerator is. We just take this traditional idea of tag matching and try to move it to an accelerator. So we remove the CPU from the equation. Here, like there are examples of using FPGAs to offload tag matching assets. But these approaches usually run into the problems of, okay, tag matching is not adapted to our architecture. Then we have another approach in hardware, which is having some space in your die in the network card to perform hardware tag matching. This is great, it's hardware uploaded, but here there are certain vendors that, for example, don't handle unexpected messages as it's most costly on their hardware. So it's a bit of a mixed bag. So here, when I introduce now our approach, optimistic tag matching, here we are trying to gap and mix these two groups and at the same time solve this challenge we have here, which is how can we make an idea, how can we extract parallelism from tag matching for being able to offload these to highly parallel architectures, like the ones we commonly find in network cards. So here we have the problem that the constraints MPI has serialized the tag matching, and we need to extract parallelism. So how we do it? So for that is the reason we created or we designed optimistic tag matching. This approach here, I'm gonna give a quick overview of how it works. Is we take a batch of M messages that we're gonna process at the same time. We map them to threads, but that's part of how we offload that to a specific architecture. So just here, just think as a thread, very something conceptual. Then each message, it's gonna be matching to the receives as if no one else was doing it. So there will not be a violation of the constraints by other threads. So you match as you would do it by yourself. Then we're gonna validate that the matching we've done is right. And we're gonna check if there are violations of this constraint. So if there are violations, we mark for the following phase would be to handle these violations and resolve them and make the messages that have violations have a matching receive that is not in conflict with the other ones. And finally, we will handle the protocol like eager or rendezvous. So before delving a bit into the phases, I want to say how we index the receives. As I said, in traditional tag matching, we have these queues but they are not very optimal for large messages, a lot of messages. So here we change how we do it. Here we divided the posted receives you can do in 3 groups, which are the ones that don't have any wildcards, the ones that have a single wildcard, be it the source or the tag wildcard, and the ones that have both of them as wildcards, source and tag. So each one of these kind of group receive is going to fall into a different data structure. So for the ones that don't have a wildcard or have just a single one, they fall into different hash tables that use the source, the tag, whatever they have available to calculate the hash. Then when you don't have any data to perform this this hash, you are just put on a linked list. Okay, so seeing this, how tag matching works? So from the 3 phases I mentioned before, we're gonna start with the optimistic matching phase. The first one is when we have to match a message as if there were no violation by other threads. So what we do here is we search optimistically for a match respecting this constraint C1 that I mentioned before, which is a single message could match multiple receives. We match to the receipt that was posted first. So how we do is here. So so every time we post a receive, we have a monotonical incremental counter that is marking the receive in a certain order. So it's very easy for us to know within a single thread what receive from our possible candidates was posted first. So in this example, I'm gonna just say that we have 2 possible candidates, but possibly we could have up to 1 per index data structure. So let's say in this example, the receive that was posted first was the one missing the tag. So that's what thread 0 matches to. So we repeat this at the same time for all the messages we receive, like I said before, map to these threads in our architecture, but that doesn't make sense now, but I'll talk about that in how we offloaded the approach. But yeah, so we have each message to each receive. So now we go to the second phase, which is the conflict detection. So now we have to check if we are violating the constraints between different threads or different messages. So here, as we are already making sure that the C1 is already not violated, now we validate with C2, which is the other way around. We check if we have multiple messages matching the same receipt. So to do so, we looked and we see, okay, so we have these 2 different messages matching to the same receipt. So now we have to make sure that only one of these messages can match to that one. So how we do this? So here the threads are picking the messages in the order they arrive. So we know that a thread with a lower index is going to be correspond to the message that arrived first. So that means thread 1 would be the one that should win that conflict detection, meaning that the message in this thread is the one that should be mapped to this receipt. So now we mark every other thread as you have to find again a receive, as the one you have right now is not valid, and we violate the constraints of MPI. This is what we now handle with conflict resolution. We have a couple protocols I'm going to explain. So when we have in this case, continuing the one we had before, we have to make sure these 2 threads, 2 and 3, have a new receive. So how do we do it? So we have 2 ways of doing this. The first one is what we call the slow path, in which we have to partially synchronize with the thread before to check that the receive we want to take is not taken. This is bad because we are extracting parallelism with optimistic time matching, but if we have to run into the slow path because we had a lot of conflicts in our data structures, now we have to trigger this path that will serialize again the approach. So we want to not do this as much as possible. So we came up with what we call the fast path, which is an specialization of when we have a sequence of what we call compatible receives, which are the receives that fall into the same bucket within our index data structure because they have the same source and tag. And we have all the threads that are in conflict. trying to match to the same receive, we know that if we just shift the thread by its ID, we're gonna be matching with different receive that are not in conflict with each other. So this is basically what we do in the fast path. Okay, so continuing with the example, now we've done the slow or the fast path, we set up the receive corresponding to its message. So tag matching is done. Okay, so now how we map this to an architecture. In our case, we've been using the data path accelerator, which is embedded lightweight processor you find in the Bluefield 3 DPU from NVIDIA. This is a multi-core processor, has 16 cores, 260, 56 threads. But the most important part here is this is embedded on the network card in the data path. So we have also direct access to NIC interrupts, NIC doorbells. So we can issue and receive RDMA operations from this accelerator. How the DPA works, like this is a fast introduction. So basically this is an event-based accelerator. So instead of running a task when you say so, it waits from an event. Here an event would be a cookie when you receive, well, a completion notification in an RDMA completion queue. And when that happens, the DPA is set up a piece of code that is gonna run when the message arrives. In this case, the thing we're gonna map here, I'm gonna show next, is the whole tag matching process, optimistic tag matching process. So every time we receive a message, which generates, as I said before, a cookie, a notification, we run this whole thing I explained before. So to do that, we also have to share the NIC resources. We have this completion queue, which is limited in size, it's a ring. So every thread, it's matching in a certain message, a certain cookie. And every time it finishes, it strides to the next one within its ID. So this is just a little bit of how it's implemented. So also one of the, as I said before, the DPA has access to the NIC interrupts and doorbells. That allows us to handle the protocol within the DPA, which is very important for our implementation, as it allows us to completely remove the CPU from the equation, as I said at the beginning with the goals. So super important, super nice. We also had some kind of some added implementations to our approach. So the first one is we calculate the hash on the sender when we send a message, as it's independent, so it doesn't use the information that is on the DPA. So as the DPA is very lightweight processors, we don't want to do a lot of operation there, just the necessary. So if we calculate the hash on the sender, we save that on the DPA. Another thing, and that knowledge optimization we made, I think is the most important one, is what we call early booking check. So when we are on the optimistic phase, instead of just saying, okay, I'm matched to this receive, and then eventually I'm gonna validate it's the one I can take on the conflict detection and then resolution. Every thread or every message that matched or maps to a receive marks that receive as being taken. So instead of waiting for conflict detection and resolution to find another one, you can still do it in the optimistic matching phase. So we'll reduce the number of conflict we find. And finally, as we're gonna have a lot of threads, removing entries from these queues, well, from these index data structures, we're gonna, instead of remove every time a thread has to remove a poster received from the data structure, it will mark it as to be removed, and eventually one thread will do the cleanup. So in this case, we don't have contention, as we're gonna have a lot of threads, around 64 or 128 normally, doing the tag matching. Okay, so as I said before, a very important part of how our approach will perform is based on if we have many collisions in the data structures we use for that. So to analyze if our approach will be performant, we set up a group of 16 MPI proxy applications that have different communication patterns, like halo exchange or multi-grid solvers, and we analyze how they behave with our approach in terms of collisions and queue depth. So for that, we develop a simple trace analyzer for our approach, in which give us the following results. So we have here a different number of bins. So for the first plot, we have 1 bin would correspond to the traditional matching approach, just having the list. And then we have 32 bins in the hash tables and 128. So we can see here that for 1 bin, so that would be the traditional approach, the queue depth is relatively high, more so compared to the other rest, and with the rest when we increase the number of bins. So as a takeaway from here, we can say that the more bins we have, we are less likely to see any collisions, which is great, because as I'm gonna show now in our message rate benchmark, our approach is comparable performance to the CPU, what is software tag matching, when we don't have collisions, which is this blue column. So if we are able to argument that, as we did before, okay, so we're not gonna see many collisions. Our approach, it has a good performance. It has comparable performance to doing this on the CPU, and we have the extra benefit of being offloaded. The problem arises when we have collisions, as having collisions with us make us use either the fast path here, the middle column, or the slow path, which already had like about a little bit than half the performance of software tag matching, and that's like, it's not great. So following our argument before, we don't see many collisions, more so when we keep increasing the size of the index of the hash tables. So our approach is something we could be used. So that would be parts like the whole project we did. So as a fast recap of what I've shown, I first introduced how traditional tag matching works and what are the constraints we have to fulfill with any kind of optimization into tag matching we do. Then I introduced how our optimistic tag matching approach, how we do it in a way that extracts parallelism from all of this. And finally, I've shown some results about the collision rate to argument that our approach is useful as when there are no collisions, and we cannot find that with certain kind of group of applications. So thank you so much. So if you have any question, please let me know.